Okay, good day everyone. We'll be looking at problem 616, which is gotten from the thermodynamic textbook, that is molecular thermodynamics of fixed equilibria, 3rd edition. So we'll be looking at this particular problem. So the question is, at 300 Kelvin, some experimental data are available for dilute liquid mixtures of components 1 and 2. When component 1 is dilute in an excess of component 2, the Henry's constant H subscript 1 of 2 is equal to 2 bar. Then when the second component is dilute in an excess of 1, the Henry's constant, that's H subscript 2 of 1 is equal to 1.60 bar. So now the question is, estimate the vapor composition which is in equilibrium with an equimolar liquid mixture of component 1 and 2 at 300 Kelvin. And again, they say we should assume that the vapor is an ideal gas. So now they gave us a supporting data that is at 300 Kelvin, the pure component vapor pressures, which is something as the saturated vapor pressure, are given us. Pure liquid 1 is 1.07, pure liquid 2 is 1.33. So now we are going to enter proper to the solution. Let us solve this particular problem. But before doing that, we have to list the data given to us from the problem. So we start by writing our data. So the first data there is our temperature was given to us as 300 Kelvin. Then the second one, the Henry's constant of 1 in excess of 2 was given to us as 2 bar. Then the Henry constant for component 2 in excess of 1 was given to us as 1.60 bar. And again, we are given the saturated vapor pressure as for the first component, we are given this as 1.07 bar. For the second component, it was given as 1.33 bar. So now, and again, from the equation, they said that that the liquid is equimolar. So that shows that means that our X1 is 0.5 and our X2 is 0.5. So what we are looking for is, they say we should find the vapor composition. That's, we are looking for our Y1, which is, and our Y2 as well. So these are what we are looking for: the vapor composition of the first component and the vapor composition of the second component. So now we have our data. The next thing is we are given an assumption here, which is they said that we should assume that the vapor is what ideal. So we write our assumption. Assumption is the vapor is an ideal gas. Yeah. So after this, we now recall that from equilibrium, that the fugacity of component I in the vapor phase is equal to the fugacity of component I in the liquid phase, which is also the same as phi I yi p equal to gamma I si f I naught. So why our phi I here is the fugacity coefficient of component I, the yi is the vapor composition of component I, the p here is the total pressure. Also here, this is the activity coefficient of component I, the liquid composition of component I, and the fugacity of component I at what standard state. So, but from the assumption, since the vapor is ideal gas, therefore our phi I is equal to 1 and f I naught is equal to p I x. So this above equation will now become y I p equal to gamma I s I p I So let's call this equation 1. So now the next thing we have to also recall that the fugacity of a component in a liquid mixture is given as the activity coefficient multiplied by the liquid composition multiplied by the fugacity of the component as the standard state, which is also at the standard state. So from here we have to make our activity coefficient the subject, which is gamma I equal to Fi L all over Si Fi naught. So what now the next thing to do is we have to find a way to relate our activity coefficient to the Henry's constant given to us for the two components. So what we do now is at infinite dilution we have to relate gamma I at infinite dilution to the Henry's constant. Now we have our activity coefficient which is equal to the fugacity of the component in the liquid phase divided by the liquid composition of the component and multiplied by the fugacity of the component at the standard state. So now we have to find a way to relate the activity coefficient to the Henry's constant. So to relate this to the Henry's constant, so we have at infinite dilution, this is equal to taking limit as the liquid composition of the component tend to 0, taking limit of the right hand side. So we have this. Now it will now become this equal to this is a constant, so we have to factor it out. We have our limit as the composition tends to 0. Then we have this all over this. So taking this limit, what we now have is this equal to 1 over Fi naught Hij. So this is equal to this equal to Hi of j over Fi naught. But Fi naught is equal to Pi sat. So this equation will now become this will now become this all over Pi sat. So with this, we can comfortably calculate our activity the activity coefficient of the two components at infinite dilution. So making use of this equation, let me call this equation 2. Making use of this equation, we have our gamma 1 at infinite dilution to be equal to H1 of 2 all over P1 sat, which is equal to our H1 of 2 is 2 bar, and our P1x from here is 1.07 bar. So dividing this, we have our gamma 1 at infinite dilution to be 1.869. The same thing applicable to the second component. So we have gamma 2 at infinite dilution to be equal to H21 over P2 sat. So this will give us, our H21 is 1.60 bar upon our P2 our amplitude sound is 1.33 bar. So dividing this over this, we have 1.203. So now we have the activity coefficients of component 1 and component 2 at infinite dilution, but this is not what we need to solve this particular problem. So we have to go ahead to calculate for the activity coefficient of the components in the mixture, which is this. This is what you are looking for. We don't need this. We don't need this, but we can actually use this to get this by making use of Van Laar equation. So according to Van Laar equation, using Van Laar equation, Van Laar equation states that ln of gamma 1 is equal to a prime all over 1 plus a prime over b prime s1 over x2 all into square. So let me call this equation 3. So similarly, ln gamma 2 is equal to b prime all over 1 plus b prime over a prime s2 over s1 all raised to 2. So let me call this equation 4. So this equation is Van Laar equation. So this equation will help us to get the value of gamma 1 and what gamma 2, which are the two important parameters we need together with the equilibrium equation to get the value of the y1 and y2, which we are looking for. So from here, we need to get the values of our a prime and b prime, and also at infinite dilution, gamma 1 is equal to a prime. Understand? So it's equal to a prime. Sorry. So a prime is equal to ln of gamma 1 at infinity. So which is equal to the ln of our gamma 1 infinity is equal to 1.869. 1.869. So our a prime will now be taking the exponential of this, exponential of ln 1.869. When you do this, you have our a prime to be 0.625. Okay, this is what it is. Okay, yeah, this is what it is. Oh, sorry, I just realized something. Okay, from here, I'm so sorry. So our a prime will now be ln of this is equal to 0.625. Yeah. So the same thing applicable to b prime. To get b prime, we have ln gamma 2 infinity equal to b prime. So this will be b prime equal to ln of our gamma 2 infinity is 1.203. So solving for this, we have our b prime to be 0.185. So now, since I have these two things, we now have our a prime and we now have our b prime. So we are now going back to equation 3 and equation 4 to get our gamma 1, which is the activity coefficient of component 1 in the mixture, and our gamma 2, which is the activity coefficient of component 2 in the mixture. So from equation 3, from equation 3, ln gamma 1 is equal to a prime. Our a prime is what? 0.625 upon 1 plus our b prime is now 0.185 over. Oh, so equation 3, from equation 3, a prime is 0.625 0.625 upon 1 plus a prime is 0.625 upon b prime. B prime is 0.185 multiplied by s1 over s2, which is 0.5 over 0.5, which is something as 1. So all into all squared. So when you do this, then now our gamma 1 will now be taking exponential of both sides. It will be exponential, which are into 0.625 over 1 plus 0.625 over 0.185. Of course, this is 1 squared. So when you do this, our gamma 1 will now be 1.033. Similarly, we also do it for gamma 2. So from equation 4, where gamma 2 is equal to b prime. Our b prime is this 0.185 upon 1 plus b prime, which is 0.185 over a prime, which is 0.625 multiplied by s2 over s1, something as 0.5 over 0.5, all squared. Then our gamma 2 will now be taking exponential of both sides. You have 0.185 upon 1 plus 0.185 over 0.625, all squared. So solving for this, we have our gamma 2 to be 1.116.
Okay, so from our equation 1, we know that YIP is equal to gamma IXI PIX. So for component 1, it's going to be YIP equal to gamma IX1 PIS. And for component 2, so let's say this is 1. For component 2 is going to be Y2P equal Y gamma 2 X2 PIS. So we have to be able to get so for us to be able to get our Y1 and Y2, which is the molar fractions of the sample in the vapor phase, I want to divide equation 1 out of 2. So we are going to get Y1P on Y2P equal to gamma 1 X1 P1 saturated all on gamma 2 X2 P2 saturated. And we know that this is going to cancel out. Our X1 is 0.5, X2 is 0.5, our gamma 1, we had it already to be 1.033, then gamma 2 to be 1.116, then our P1 saturated is 1.07, then P2 saturated is 1.33. So substituting all these parameters into the equation, we get Y1 on Y2 to be equal to 1.033 times 0.5 times 1.07 all over the gamma 2. We have 1.116 times 0.5 times 1.33, and from this we are going to get Y1 on Y2 to be equal to 0.7 From this, we can get y1 to be equal to 0.7447 of y2. And from there, we know that we are talking about an equimolar mixture, liquid. Okay, but we know that y1 plus y2 is equal to 1, making y1 equal 1 minus y2. So let's call this equation. Okay, so we know from here we are going to get y2 equal 1 minus y1. So let's call this equation star star. Then this one will be our equation star. So equation star star into equation star, we are going to get y1 equal 0.7747 into bracket 1 minus y1. And from here, grouping like terms, I'm going to get y 0.7447 minus 0.7447y1. I'm going to get y1 plus 0.7447y1 equals to 0.7447. And from this, we are going to get y1 to be equal to. Okay, so from this, we are going to get 1.7447y1 equal to 0.7447. Then y1 is going to be 0.7447 divided by 1.7447. And I'm going to get y1 to be equal to 0.427. So we can put this back into our equation. This one was equation star. Yeah, you can put it back into equation star. Then you get our y2. So we know that y2 is equal to 1 minus y1. So y2 will be equal to 1 minus 0.427. And our y2 will be equal to 0.573. Okay, so from everything we get to know that the vapor composition for component 1 in the mixture, that is y1, is equal to 0.427. And for the vapor composition for component 2, that is y2, is equal to 0.573. Yeah. So thank you very much for watching. My name is Rebecca Kofi.
And my own name is Elochukwu Okoye. Thanks for your time and thanks for watching. Thank you.